the theoretical side of things, but also in the nitty-gritty manufacturing. Honestly, most of the time, you could make anything you want on the computer. That doesn't mean you're going to be able to just pop it out. So we want to like be able to do basic, make stuff out of cardboard, use like different
Yeah,
robotic
the
stuff.
lectures are only going to be in for like a month. After that, we're just going to be building. We're going to be in the makerspace. But we're going to throughout next week, I'll be in the makerspace. Angel will be in the makerspace working on projects. You guys are free to come and help us with that and be a part of it. But I'm going to start the lectures.
Yeah.
So yeah, all of these lectures, they come from three books. Two of them are engineering books, one isn't. The one that's used by the American Association of Aeronautic Engineers is the first one. It's called Aircraft Designed by Raymer. You can find it anywhere. Fourth edition and above is still accurate today because these are really old books. Um, and yeah, I recommend them for anyone who's interested in aerospace or aeronautics, right? The second one is the book that's recommended by our faculty advisor, Dr. McDaniel. It's I haven't read it completely, but it gives like it teaches you vaguely about all things aerospace, both in aeronautics and astronautics. So I'd recommend it. And the last one is the aviation mechanic. It's not an engineering book, it's a mechanics book. But when we do test our planes and we make sure that when they come back from flight and there's something wrong, there's something broken, that teaches us how to fix it and where it went wrong. So, I mean, they're all pretty good books. If you guys get any of them, please get Raymer, the first one. It's really good and teaches you almost everything about aircraft design.
I probably take
Um, yeah. What?
like how that anyone want to take. You say, what are you?
This is recorded.
Oh.
Like you can see it up there as well. Okay. So there's a lot of different types of planes, and there's different planes by design, different planes by aileron, by wing size, and we're gonna be going over really only two types of planes in aero building them and in this lecture. The two types are civil aviation, which is kind of like this Piper that you see down here, and the other type is military planes. That's more like a Corsair or F-15s, because those are the two main types of planes that were tested on when we do compete. This year we're not competing because funding, but we're hoping to go back to competing next year. So basic aircraft parts. The main part of every plane, it doesn't matter if it's a B-2 or just like a simple Cessna, is the fuselage, which is the main body of the plane, the landing gear, the power plant. The power plant refers to both the motor and the propeller, so just kind of sign like this. And the empennage. The empennage is the tail assembly. It includes, on some planes, it would include the horizontal stabilizer, which is this part down here, and the vertical stabilizer. But planes like the B-2 obviously don't have a vertical stabilizer. Aircraft components. So for motions of aircrafts, there's a few main surfaces that you guys have to know. There's ailerons. Ailerons control a certain movement called roll. Ailerons move opposite to each other, so what they extend like this. Flaps, which are this control surface down here. Flaps are used to control speed and generate drag if you want to reduce speed and generate lift if you want to take off. Flaps work in unison to each other, so they extend downwards or upwards, usually by 30 degrees, a deflection by that amount. The vertical stabilizer controls a movement called yaw. I'll show you now with that plane. And the last is the elevator. The elevator is what controls pitch on an aircraft.
You want to do the demonstration?
That bit. And then elevators would work in union to each other. So there's three types of movement on traditional aircrafts that have tails. Angel, do you want to like show?
Oh yeah, yeah.
So planes move around their center of gravity, which would be the white part.
Basically, this white part right here. Imagine that's the gravity.
A roll would be a movement like this.
Don't worry about that.
That's a roll. Roll would be movement like this on an aircraft. It's caused by the ailerons moving in opposite directions. Exactly how lift is generated on an airfoil is next Monday's meeting, but yeah. The second type of motion is pitch, which is because of the elevators in the back. The plane would pitch up or pitch down. Yeah, the elevators would deflect, and then and it moves around the center of gravity. All movement happens around the center of gravity on an airplane. The last movement is yaw. It's caused by the rudder, the part that Angel's holding now. And the plane would move literally just this way around the center of motion, center of gravity. So yeah, on designs like the B2, for example, that don't have a tail, what they do is that the ailerons and the elevators are mixed. They're called elevons. One design flaw that the B2 does have is that because of its, what do you call it?
Picture of the B2.
Here, for example, these are elevons. Whenever it tries to roll, the B2 would naturally go down because its center of gravity is ahead of the control surface. So that's just one design flaw. What is it? This is for airframes. Airframes would refer to this part, the wing assembly. On each wing, this is what we're seeing, is a spar. The spar is this part of, just like a wooden part that connects the wing all the way to the body of the aircraft. The wings connect all the way down, and they're the main structural unit, the primary structural unit for longitude to prevent shear force on a plane. The secondary is stringers. Not all planes have stringers, but all planes with wings will have the spars. The ribs are the shape itself of the wing that form lift on an aircraft, and then after that you have ailerons and you have wing flaps.
I'm gonna pass around one of the airfoils you guys would like to see, just like check out everything we sustain.
And yeah, you just have, here's like another picture of just like airframe assembly. Airframe also refers to the structural parts of the plane, but that's not going to be today's focus. Like the body of the aircraft, actually forming the fuselage. So this is aerodynamic. This is an airfoil. That's what the shape of the wing is. This is the main portion responsible for generating lift on an aircraft. The way that lift is generated is that wind is passing on the airfoil on the top surface and on the bottom surface. But it's because of the curve being greater on the top, air is traveling faster on the top surface, which is generating pressure, like a negative pressure differential is what it's called. We're going to talk about that on Monday and the actual equation for it. But the negative pressure differential felt by the airfoil is what causes lift upwards. On aerobatic planes, like you've seen it, like Red Bull planes that go upside down, the airfoil is perfectly symmetrical, and how those generate lift is also going to be next time. All you need to know for the airfoil itself, though, is that the most front part is known as the leading edge. The back part is called the trailing edge. In between them, there's an imaginary line called a chord line. And what do you call it? The difference, the midpoint between the top surface and the bottom makes this called the mean camber line. Andrew, you want to talk about this?
You can start.
Okay, so propulsions. Propulsions is one of the subsystems for aero. It's basically force is formed by their motor rotating, and what happens is that the cross section of the propeller is an airfoil itself. So this shape is the cross section of the propeller, and that's what's generating a force forwards. Let's see, propeller pitch would just represents the distance that it travels per rotations. But the propeller, one full rotation of the distance of that is what's called the propeller pitch. That's how we would measure that theoretically, because actually having to measure that would require dynamic testing environments, which FIU does not allow us to have.
All right, can I make
Would you like?
Yeah.
Okay.
This is if you go back.
Oh, okay.
So one of the considerations, at least that I want to approach this year, is the angle of attack. So when planes first came into existence, they had done something called fixed pitch propellers. Does anyone know what that means? That basically means that the angle of attack that you see right here was fixed and it did not change at all. And this had a few caveats. One, which is that engineers had to optimize the pitch according to the altitude. So we all know that like the higher up in the air you go, the less dense the air is. So what this means is that for planes, in order to travel at higher altitudes, what they need to do is that they need to pull more air towards them. And so if you were creating a high altitude propeller plane, you would want to have a higher angle of attack in order to be able to pull more air. The analogy I give people is that when you guys swim, right? Do you swim? Do you do like a breaststroke like this or like this? Which does your hand go like this or like this? Like right here. You could think of an airplane's propeller as doing the same thing. When you have your propeller's pitch very high, it's the same thing as when you're swimming through the water and you can imagine that propeller is cutting through the air and thrusting air behind it, which is why it makes it go forward. But if let's say you are gliding through the water, have some velocity, do you have your hands like this while you're going forward, or would you at least have them like this? You're creating a lot of drag due to the air when you're moving like this. So one of the issues that's caused by fixed pitch propellers, let's say you want to have characteristics like you want to be able to take off really fast, or you want to be able to have a super high climbing speed. The issue or like the requirement behind that would be you need to have very high pitch because you want to increase and maximize the thrust you have. But the issue, the trade-off is that it's the same thing. When you're in the water and you have your hand completely pitched forward, that creates a lot of drag on like between you and the water. So this actually could limit, like through parasitic drag effects, the speed that like the maximum operating speed of the plane. So what engineers, especially around early World War II, you guys might know things like the British Spitfire or the P-51 Mustang. They developed propeller pitch control systems in which they made the motion of the propeller's pitch independent to the actual like mechanical, like the fuselage itself. So the way this works is that they use the engine pressure, or like the pressure of the oil as the oil heated up, that would expand. And naturally, as the plane had to climb more, it would use more engine power, the oil would heat up. And so what that told the engineers is that, okay, they need to increase the pitch because it's probably going higher in altitude, and therefore like they need to pull more air. Or if the engine was going extremely fast, you were able to control that so that you experience less parasitic drag. One of the things that in our previous projects and previous planes with the club, we never had any sort of propeller pitch controls. So, you know, motions guys, I'm just saying, like, we're going to want to explore that.
So this is flight performance. The image that is right here is an, what do you call it? It's the speed indicator that's on all aircrafts, both civil and military. The main important things to know is that the white arc that you see here is the stall speed. Stall speed is the minimum speed that we need to take off with, assuming all conditions are met, like there's no weight issues on the planes or it has enough weight to take off. The never exceed speed is this red line here. That's the speed that if the plane passes, it will begin to have structural effects on the plane because as a plane is moving through the air, it experiences pressure and that pressure will begin to rip apart at the plane structure. The best angle of climb is just noted by Vx. Vy is the best rate of climb, and the glide ratio is how much forward a plane moves for every feet it goes down. So if a plane were to just suddenly, its engine were to suddenly stop right here, if it went down, let's say 10,000 feet for every 18,000 feet, the glide ratio would just be this ratio given by this 110/18. And usually we want our planes to have a higher glide ratio. Gliders have a much better and stronger ratio over like 20 or so. So yeah. The green arc is just like the regular operating range of the airplane, and the yellow arc is only recommended for laminar flow. That should be everything. So these are just general abbreviations. Next week, we're going to be using a software called XFLR5. Here's a picture of it. Some of the abbreviations you have to know for XFLR5 is CG, which is just center of gravity. On a plane, the CG is also shown by this symbol here. You'll see it somewhere on the fuselage or on the wings. Maximum takeoff weight is MTO. Lift to drag ratio is L/D. Specific fuel consumption, this relates directly to the engine itself. It's just SFC. Equivalent to true airspeed. The difference between equivalent and true airspeed is just that when you're up, let's say 30,000 feet in the air, you experience so much pressure and there's a tense pressure in the air that causes you to slow down a little bit. True speed is the actual airspeed. So equivalent speed is what you're experiencing the speed that you would be going at if you were at sea level without the pressure difference that you have in the air. CD is the drag coefficient, CL is the lift coefficient, and alpha is angle of attack. These are more relevant for Exaflare 5. And we'll show you how to use that next week. So this is just like to get ahead of next lecture. Next lecture is not going to be like vocabulary. It's actually going to be math based, and we're actually going to have equations for you guys to do. This is just nomenclature, but there's four forces that a plane experiences always. There's lift, which is a force upward that's caused from the wings. You have weight, which is directly downward. It's the CG. It's experienced from the CG. There's thrust, which is from the engines going forward, and there's drag that's caused from either the shape of the plane or the material that the plane is made out of, pulling the plane back. When we're flying at a smooth pace without any like alterations, all of the thrust is equal to drag and lift is equal to weight. So, and then obviously for acceleration, thrust has to be greater than drag, lift, and for level flight, yeah, lift has to equal weight and thrust has to equal drag. So yeah, this is more for like attendance. So let me connect it. Anyone have any questions or like about anything? It's fine.
Oh,
Yeah, once. Anyone hasn't seen the Aero? Yeah.